Hey, it seems like we're live. So hello to the internet. Today I'm gonna be streaming myself studying some advanced programming in the Unix environment. This is mainly gonna work by me reading through the chapters and writing down some notes on my understanding of the topic and trying to explain what I understand verbally as well as I write things down. As I mentioned, the book I'm going to be following along to is Advanced Programming in the Unix Environment, and this is written by W. Richard Stevens and Stephen A. Rigo. If anyone wants to study along with me, you can get the book, but if you don't want to, I guess that's your personal choice. I'm going to start off with chapter 1. I'm not going to look at any prefaces. And chapter 1. This is mainly an overview about the Unix system. So in 1.1, mainly it describes that operating systems are what your computer uses to run programs. No matter what the software might be, it runs the software on top of a layer, which is it runs it on a layer on top of the hardware, but called the kernel. Basically, your computer has its hardware, and the only thing that has access to this hardware is the kernel. Now, to interact with the kernel, you need to perform system calls. Now, these could be things like, hey kernel, my program needs more RAM. Please give me RAM. Now, system calls are not the only way to interact with the kernel. You can also interact with the kernel through some library routines. Library routines. It's not good looking, but that's fine. You can also interact with it directly with the shell. But mainly, what you're running on your PC are different applications. Now this can be all sorts of things, video games, your web browser, pretty much anything you run on a computer is an application. You can run real system calls from an application, but usually the easiest way is to just run library routines that are part of the language you're using. That's mainly what it says here. Applications are free to use whatever way they want to interact with the kernel, but the kernel is the main part that interacts with the hardware. Unless the kernel gives permission to the applications to use it. And even then, usually the kernel handles the drivers in most modern systems. The Linux kernel, kernel is how one interacts with the hardware of one's system to interact with the kernel. You must use either directly or indirectly system calls in most applications. You use standard library functions to interact with the kernel. Now, most of you probably know this, but Linux kernel is used by, probably most familiar is the GNU/Linux operating system, though it's also used in other cases such as Android. Now, the next thing the book talks about is logging in. 1.3, logging in. And basically it says when you log in, you use a username and password. This password. And the main information about the person is in the password file. So the password file is /etc/password. And this has a list of files, or a list of entries like such. So dot sar x 205 Stephen Rego /home/sar /bin/ksh. And mainly what this says is the username, UID, group ID, some alias like name, or how you want it to appear, their home directory, and what shell they like to use. And another entry which we'll get back to later. Now, once you log in, so we'll leave user ID and group ID to later, but once you log in, you, depending on the system, you either get a GUI or a shell, which is a command line interface to execute commands. So you have the shell to execute commands. And which shell you like to use is determined by that. The most common shell, such as the default on Ubuntu, is the Bourne shell. aka bash. And yeah, that's the most common on others, but you can also use other ones such as ZSH, or even write your own shell if you wish. So, and another note is that by default on Linux, the password is encrypted and stored somewhere else. And this is all managed by the kernel. You ask the kernel to log in, and it allows you to log in, or otherwise, it doesn't let you log in. Now, quick notes on files. Files. And directories. In Linux, files are done as a hierarchy. This is how most people understand it. It kind of goes in like a tree. So you have your most important directory, which is slash. And then within slash, you have different files. So slash bin, slash home, slash Etsy. And then each of these will have things inside them too. So slash admin, slash user, slash bob2. Yeah, so basically it's hierarchical structure. And the different names here, directories, filled with files called file names. And these file names can use any character except for the / character and null. So any character you can think of, whether it's $, $, B, enter, or EOF. Well, that's usually null. This character, backtick, squiggly line. Basically, any character, no matter how obtuse it can be called. Typically, though, it is best practice to use A to Z. Use anything. Best practice. Use only A to Z, A to Z, 0 to 9, dot, dash, and underscore. Now each directory also has 2 files in it. By default. And these are 1 dot and 2 dot dot. So this just points to the folder you're in. And this double dot points to the parent folder. Current folder. Now at the root directory is the only time this changes, and dot dot just refers to dot. So at slash dot dot equals slash dot. Only time is different is at root. And path name is what you call the extended notation. So that would be something like slash home slash bob2 or dot slash bob2 slash downloads or anything else. These are called absolute and these are called relative. So absolute is when a directory a path name begins with the root directory slash. Now, to list all the files in a directory, it's not too difficult at all. You can write a simple command that does this. Now, the authors have decided to use C for the commands. C command or C program to show all file names in a directory. Now, so the program is basically int main, int argc car star argv dir. So to read dir, we need to tag include dir int.h dir star dp and struct dir int star dirp. Now we'll just add some quick error correction. If argc not equals to error quit usage ls dir name. Now we'll run if vp equals open dir argv1 equals null persists error codes not open percentage s argv1 and basically this opens the directory that we specified and saves it to dp. And v1 and if it can't open it, then open dir returns null and you get an error. Otherwise, we're left with dp. Now we use a while loop. While derp equals read dir dp not null, we want to printf percentage s /n derp t name and we close dir dp when we're done and exit 0. Now we also have to include appu.h from their included files, which basically contains any functions you might have used that are not included. So basically, what this program does is it assigns some memory for a pointer to the directory name. It reads the number of arguments and the arguments. So that would be ls argv or 1, which would be, for example, ls/home. It assigns a pointer to the directory structure and a dirent structure. It checks that you entered command correctly. And if that's okay, then it continues, opens the file. If that's okay, it opens every it opens the next file within the directory. So reader, I think, basically saves within dir. The next file that it's reading, so it saves the index that it's on. Then when you run it again, it goes to the next one. When you run it again, it goes to the next one. And then once it's done, it says there's none left. It returns null. And you can continue. Now, while it reads the files, if you can, it reads the directory entry and prints d_name. Then it closes it and exits. Okay. So if you wanted to actually run this, you would gcc the file, run gcc /myls.c, and if you were to run /a.out/dev, you would get a result like this. Result cd-rom no 0 and whatever other files there might be. Now if you try to run this in a file that doesn't have permission /a.out/etc/ssl/private gives error, permission denied, and /a.out. For command, just from now on, any commands run by a regular user, as in the book, I'm going to use $sign notation. And if you do that to a fake directory, like /fake/directory, it'll just give error, not a directory, can't open. Now, in the book, it basically explains what I was looking at. So, a couple notes. Working directory. That's just the folder you're currently in. So, if you were in a terminal, you could do that by just printing path, or you could run cwd, current working directory, and home directory. That was defined in the /etc/password file. That depends on the user. So for root, it's /root. For bob2, it's /home/bob2, or whatever else it might be. A quick note: when it comes to files, in Linux, basically anything is considered a file, at least to a certain level of its abstraction. Most things can be accessed as if they were a file. So you have file, that's a file, like .text. A folder is considered a directory file. You can have symbolic links, which are different types of files. You can also have network files and other types of files, but that's covered in a later chapter. Now 1.5. Input and output. So when you're running a program, you open some number of files, which are stored by the kernel of what files you're currently looking at. And file descriptors are the indices of those files in whatever order they are opened in. So when you run a file, when you run a program and you are working with any sort of inputs and outputs, those are controlled by a program, or by the kernel. The kernel keeps a list, of open files. So 0, 1, 2, 3, and first file, second file, third file, some file, ... And by default, the kernel has 3 files open by default. Which are not actual files on your disk, but, well, not necessarily, but the kernel gives you 3 files. File descriptors are the indices of those files as controlled by the kernel. By default. Zero corresponds to standard input. 1 corresponds to standard output. And 2 corresponds to standard error. Now what do these mean? So let's say you open a terminal. The standard input would be your keyboard, basically. Typing stuff with keyboard. And blinking cursor thing. So the input is the keyboard. Your keyboard. The output in the terminal is basically the results of what you write. So maybe you press cat or echo hello world, and it would write hello world. Now standard error also goes to the terminal and prints out things in the terminal. So this is called std in, std out, and std error. And these are just constants kept as part of the kernel. The reason they do this is because in Linux this is the standard, but theoretically it is possible that somebody might make another Unix-like operating system where that's not quite the standard, and yeah, that's basically why they do that. You can also change what std in, std out, std are when you run a program. So for example, if you run something like ls file.text, then it runs ls and std out is now that file instead of the console. Okay, so next it talks about unbuffered IO. So unbuffered IO is provided by functions open, write, read, lseek, and close. So, for example, we can read from the standard input and write to the standard output. So, program to read std in, write to std out. So this would basically be something like echo. So include view.h, define buff size 096. Now because this is unbuffered, we have to choose our own buffer. So we choose the buffer to be 4096. So int main void int n car buff size, and while we read the user input, we continue to write the output. So while goes read std in file no buff size greater than 0. So while the text we put into the terminal is not blank, if write std out file no buff n not equals n, error sys write error. So it writes to the standard std out, standard output, which in this case depends on what we decide to be. By default, it would be the terminal. It outputs buffer, which is given here, and n, which is the length of the standard input that we read earlier and saved. Yeah, so it saves the input to the buffer and then reads the buffer out and writes it to its standard file now. And then if there's not an error, it keeps doing that until you write blank. Now, if n less than 0, sys read error. So if the n we get here is negative, then that means the function probably failed. In most cases this shouldn't fail, but sometimes it does. And then exit 0 if we have no error, and return. Now we could compile this program, and we can do /a.out, and that would basically just you write a line, and then it outputs that exact line plus /a.out. Testing, and then it would just write testing. Write in with keyboard. Put by terminal. You can also use this to append or write the output of one file to another file. So for example, /a.out in file, out file. So in std out. Yeah, and this will just be copied to this file. You can also just use you can also have /a.out and just out file. Copies keyboard input to file. And now we're going to talk about standard I/O. Basically, the standard I/O functions are a way to use the standard I/O functions give us a buffered interface to the unbuffered I/O functions. This way we don't have to choose buff size as we did before. And it makes it easier to work with lines of code. So for example, things like printf and fgetS are standard functions that make it easier to work with things. So these are functions built upon the system functions that make it easier to work with inputs and outputs. For example, printf fgetS ... And as part of the book, that's included in appu.h for simplicity. As well as to just reduce the amount of code we have to write. For example, what we can do is automate the process of reading an input and make it so that you don't have to manually read the input, and rather that's done automatically by your functions here. So an implementation of this is include appu.h int main void int c while c equals get c std in not equals end of function if c std out equals eof sys output error. And if ferror std in sys input error and exit 0. Get C runs one character at a time until it gets to the end of a file, and once it does that, it stops working. But while it's not at the end of the file, it prints it to the standard output, and once that's done, it returns. Unless there is any errors, in which case those are included. Now, that's mainly quite basic material so far. Just reading and writing files without going too depth onto how it works exactly. Hopefully it's somewhat insightful. I'll probably be returning tomorrow sometime and be working. So, back tomorrow. Be working on programs, processes, and probably some other fun topics such as error handling, user identification, and if we can get to it, we can start working on signals. Okay, well, thanks if anyone actually watches this. Nice. See you guys.